Hello everyone and welcome back. My name is Mr. Kovald, and in this video we're going to go over the equilibrium constant and the law of mass action. So let's get into this. So in my previous video I talked about the rates of reactions and dynamic equilibrium. We talked about how in dynamic equilibrium the rate of the forward reaction is equal to the rate of the reverse reaction. And so when you're at dynamic equilibrium, the amounts of products and the amounts of reactants do not change, although there still is that process of converting reactants to products and products back to reactants. So that's still going on. So that's the dynamic aspect of equilibrium. But the equality is not that the number or the amount of products is equal to the amount of reactants, just that those amounts, whatever they are, stay constant. And so this brings up to the equilibrium constant and the law of mass action. So here we have a generic equation where the small letters, the lowercase letters, are your coefficients, and the uppercase letters are the substances that we're dealing with, our reactants and products. And so we can express the ratio, we can express the amounts of the reactants and products to each other as a ratio. And so what we see here is that the products are put on top. So you can see that we have these square brackets, and remember the square brackets represent concentration of that substance. So what you see here is that on the top you have the products. So you have the concentration of C, capital C, raised to the coefficient of C. So little c is the coefficient. But we're writing that as a power or an exponent. So you can see that the concentration of product C raised to its coefficient little c is multiplied by the concentration of the other product D, capital D, raised to its coefficient little d, right? So we have the products on the top multiplied by each other, and they're both raised to their coefficients. And on the bottom of this ratio, you have the reactants. And so in this case, you have the concentration of reactant A, capital A, raised to its coefficient. So the coefficient of the A here is now becomes a exponent. So you have the little a as an exponent, and so now you have that A concentration is multiplied by the concentration of B, capital B, raised to its exponent, little b, as a exponent. So what you see here is that the ratio of the products on the top, the concentration of the products multiplied by each other, raised to their coefficients, and on the bottom, divided by the the concentrations of A and B, the reactants, raised to their coefficients as powers. And so this is the expression of what we call the equilibrium constant. So constant K, equilibrium constant of a reversible reaction, is expressed in this way. And so this only occurs, this only works, this is only true at equilibrium. So you have the reaction, when it's at equilibrium, the ratio of products and reactants, the concentrations of, are going to equal a certain constant. And so why does this ratio stay constant? Well, that's because we're talking about at equilibrium. And when you're at equilibrium, the amounts of products and reactants don't change, and so the concentrations aren't going to change. And therefore the ratio of those reactants and products aren't going to change. So this K value fits with this reaction at equilibrium. And so the relationship between the balanced equation at equilibrium and the K expression is what we call the law of mass action. So if we were to change any of the concentrations here, if we were to add B or add C or something like that, then the reaction would adjust to come back to the same ratio it was in order to get that K value at equilibrium. So no matter what substances you have, or I should say how much of that substance you have, you're always going to go back to the K value at equilibrium. Okay, so let's show how to, or let's go over how to write the expression of an equilibrium constant based on what we just said. So here we have a generic equation, and here we have a real actual reaction. And so how would you write the K expression or the equilibrium constant expression for both of these? So remember, it's the products, the concentration of the products over the reactants, and the concentration of each species is raised to the power of its coefficient. So whatever the coefficient is, that becomes the power. So here we have 2A plus 3B gives us C, and that's in dynamic equilibrium with each other. So the C is in dynamic equilibrium with B and A. Okay, so how would we write the K expression or the equilibrium constant expression for this? Well, if we follow this, then we're going to put the product on top. So K is equal to, it's going to be the concentration of C. And we only have one product, so only C is going to be on top. So we have C. And the coefficient is 1. We don't write ones, but it's got to be there because we have 1C there. So the coefficient is going to be 1, right? You don't have to write the 1 here, but I'm just writing it to show that that's what the exponent is going to be. The coefficient is 1, therefore the exponent is 1. So now we come to A and B. So these are reactants, so they're going to go on the bottom. So we're going to start with A, so it's going to be the concentration of A. And its coefficient is 2, so that becomes the exponent. So that's going to be 2. And then now we're going to multiply that by the concentration of B. So we're going to put B on the bottom because that's a reactant. So it's going to be the concentration of B. And its coefficient is 3, so that becomes the exponent of B. So there you go. So then this would be the equilibrium constant expression for this reaction. So at equilibrium, we would put in whatever the concentrations are and calculate that constant. And so that number, whatever we get, should be the number that we'll always get at equilibrium, because the equation here at equilibrium is this expression here. This expression here is related to this equation. And so at equilibrium, at a certain temperature, right? So the temperature has to be a certain amount. We're going to get a certain number, a certain constant, and that's going to be the equilibrium constant. And that constant doesn't change unless, of course, the temperature changes. So this is a constant at equilibrium. It's only the constant at equilibrium. So in order to have this constant, our reaction is at equilibrium. And it's got to be at a certain temperature. If you change the temperature, then the constant is going to change. So as long as we keep the temperature the same, then this K value, whatever it is, will always be the same at equilibrium. Okay, so what about this reaction here? Well, same thing, except now we have compounds that we're dealing with. So what would the K value for this reaction be? So we just do K again. And so again, it's going to be the concentration of the products over the reactants raised to the power of their coefficients, whatever their coefficients are. So here we have NO2, so we're going to write, we have 2 products this time. So we're going to put both products on top. So NO2, so the concentration of NO2, and it's got a 4 coefficient, so that's going to be a 4 exponent. And then now we have oxygen, so we're going to multiply that by the concentration of O2. And it's got a 1 coefficient, so we can put a 1 there. Again, you don't have to write the ones, but I'm just showing you that it's a coefficient, so this is a 1. There's a 1 there. We don't normally write ones, so I'm just showing you. So now we've got the reactants done, and here we have one product. So this is the only thing we're going to put on the bottom. So we have N2O5. So the concentration of N2O5. And since the coefficient here is a 2, we're going to write that as a exponent. And so this would be the equilibrium constant expression for this reaction at equilibrium. So if we knew the concentrations of each of these at equilibrium, then we could plug those into here, calculate what K value would be at equilibrium. And that, again, should be the same K value at equilibrium no matter what these amounts end up being, right? So we'll talk more about that in future videos. I hope this video was helpful. I hope you learned something. Please like the video, smash that like button, subscribe to my channel, hit that notification bell so you can be notified by other videos I put out. And put a comment in the comment section. Let me know what you think. If you have any other questions, please ask. Thanks for joining me. Have a great day.